Look up at the night sky and you'll see stars, planets, and swirling galaxies, but nothing quite like the haunting beauty of a ring galaxy. These cosmic oddities, with their perfect loops of stars and gas, look like celestial fingerprints pressed into the fabric of space. They defy everything we thought we knew about how galaxies form, spinning in ways that leave astronomers scratching their heads. What could create such a flawless ring of light millions of light years across? The answer is as mysterious as the galaxies themselves, and today we're diving deep into 30 of the strangest phenomena hidden within these enigmatic cosmic rings. Some of these riddles are so bizarre they seem ripped straight from science fiction. Picture a galaxy where stars move in perfect unison, like dancers in a cosmic ballet, or black holes lurking at the edges of these rings, warping space itself. Others defy logic entirely, galaxies that shouldn't exist based on our current understanding of physics, or ghostly trails of matter stretching across the void like cosmic breadcrumbs. These aren't just quirks of the universe, they're clues hinting at forces and phenomena we've barely begun to understand. This journey isn't just about cataloging strange sights, it's about unraveling the secrets of the cosmos. Every ring galaxy holds a piece of the puzzle, a story written in starlight and shaped by collisions, dark matter, and the invisible threads that bind the universe together. By the time we're done, you'll see these celestial wonders in a whole new light, not just as distant swirls of stars, but as cosmic mysteries waiting to be solved. So let's begin, because the deeper we look, the stranger it gets. Most galaxies, like our own Milky Way, have a dense, bright cluster of stars at their core, what astronomers call the central bulge. But ring galaxies break all the rules. Instead of that expected glowing heart, many have nothing. Just an eerie, empty space where the bulge should be, surrounded by that perfect loop of stars. It's like finding a donut with no hole. Only in this case, the missing center is millions of light years wide. So what happened to these galactic cores? One leading theory points to violent collisions. Picture a smaller galaxy plowing straight through a larger one, like a bullet tearing through a spinning disk. The impact sends shockwaves rippling outward, flinging stars into that iconic ring shape, while the original core is either scattered or swallowed by an invisible predator, a supermassive black hole. Some researchers argue these black holes, once active, might have devoured the surrounding stars before going quiet, leaving behind only a ghostly imprint of their feast. But here's where it gets stranger. Not all ring galaxies fit this story. A few rare specimens do have bulges, defying the collision model entirely. Others show chemical signatures in their stars that suggest they formed their rings without any crash at all. That means either our theories are missing a key piece, or multiple cosmic phenomena can create these perfect rings. Every new observation twists the mystery deeper, forcing astronomers to rethink how galaxies live, die, and sometimes against all odds, reshape themselves into cosmic mysteries. At the very edges of these galactic rings, something extraordinary happens. Stars are born at a rate that defies imagination. Unlike the quiet, measured pace of star formation in spiral galaxies, these rings become cosmic nurseries on overdrive, bursting with newborn stars in a frenzy of creation. Take the Cartwheel Galaxy, one of the most dramatic examples. Its outer ring is a fireworks display of stellar birth, with regions so dense and active that they outshine entire galaxies. Hubble images reveal clusters of young, massive stars, blue giants burning fiercely against the dark backdrop of space, their intense radiation sculpting the surrounding gas into glowing filaments and bubbles. But why here? Why do these rings become such fertile ground for new stars? The answer lies in the shockwaves rippling through them. When galaxies collide, or when one punches through another, the resulting turbulence compresses vast clouds of gas, squeezing them until they collapse under their own gravity. Think of it like clapping your hands in a cloud of dust. The sudden pressure sends particles flying, but in space, that motion triggers a cascade of star formation. The ring's structure acts as a perfect trap, concentrating these shockwaves along its edges and creating ideal conditions for stellar birth. Yet this frenzy poses a puzzle for astronomers. Standard models predict star formation should slow down as gas is used up or blown away by stellar winds, but some ring galaxies keep producing stars far longer than expected. Some even show evidence of multiple generations of stars forming in the same region, as if the ring reignites itself over and over. That suggests hidden reservoirs of gas, or perhaps forces we don't yet understand, are at work, feeding these cosmic fires in ways that challenge our textbooks. Every new observation of these stellar nurseries forces us to rethink the rules of how stars are born, live, and die in the most extreme corners of the universe. Among the countless ring galaxies scattered across the cosmos, one stands out with such flawless symmetry that it almost looks artificial. Hoag's object. This celestial wonder is a near-perfect circle of young, blue stars cradling an ancient golden core, separated by a vast, dark gap that gives it the appearance of a cosmic bullseye. Unlike most ring galaxies, which show signs of distortion or uneven star distribution, Hoag's object is eerily pristine, as if sculpted by an unseen hand. Its symmetry is so striking that when astronomer Art Hoag first discovered it in 1950, he initially mistook it for a glitch in his telescope. The mystery lies in how such perfection could exist. Most ring galaxies owe their shape to violent collisions, but Hoag's object shows no evidence of a past crash, no debris, no warped trails of stars, nothing to suggest a catastrophic encounter. This has led to wild theories, from rogue waves of dark matter stabilizing its structure to an ancient instability within the galaxy itself that somehow ejected stars into this precise formation. The leading hypothesis suggests a slower, more delicate process, a gravitational ripple possibly triggered by a smaller galaxy passing nearby, gently shepherding stars outward into that iconic ring without the chaos of a direct hit. Yet even more baffling is its longevity. Galactic structures tend to degrade over time, their shapes blurred by gravitational tugs and internal turbulence. But Hoag's object has maintained its perfect form for billions of years, as if frozen in time. Some researchers speculate its isolation plays a role floating in a quiet corner of space, far from the gravitational pull of neighboring galaxies that might disrupt its delicate balance. Others propose its dark gap acts as a buffer, a cosmic moat shielding the ring from disturbances. But the truth is, no single theory fully explains Hoag's object. It's a cosmic outlier, challenging our assumptions about how galaxies evolve. Every new observation deepens the enigma, revealing subtle details, like faint secondary rings or unusual star motions, that hint at a history far more complex than we've imagined. For now, it remains a masterpiece of the universe, a reminder that some celestial mysteries refuse to fit neatly into our textbooks. Dark matter should be evenly spread throughout a galaxy, or so we thought. But ring galaxies are flipping that assumption on its head. Observations using gravitational lensing, where the galaxy's mass bends light from distant objects behind it, reveal something bizarre. The dark matter in these cosmic rings isn't smoothly distributed. Instead, it clumps in unexpected ways, pooling along the edges of the ring or even forming strange, lopsided halos around the structure. It's as if gravity itself is playing tricks on us, defying the rules we've used to map the invisible scaffolding of the universe for decades. This unevenness challenges one of cosmology's bedrock principles, the idea that dark matter, while mysterious, at least behaves predictably. In spiral galaxies, dark matter forms a roughly spherical halo, anchoring stars and gas in place. But in ring galaxies, that tidy model falls apart. Some theories suggest the violent collisions that create these rings might scatter dark matter like debris in a cosmic demolition, leaving it concentrated in patches. Others propose that interactions with unseen subhalos, smaller clumps of dark matter, could be tugging at the ring's structure, warping its distribution over time. The implications are staggering. If dark matter doesn't behave uniformly, it could mean our entire understanding of galactic evolution is incomplete. Some researchers argue these anomalies hint at hidden properties of dark matter itself. Perhaps it's not the simple, slow-moving particle we've assumed, but something more dynamic, capable of clumping or responding to shocks in ways we haven't accounted for. Others speculate that we're seeing the fingerprints of entirely new physics, forces beyond our current models that only reveal themselves in these extreme galactic environments. Every new observation adds another layer to the puzzle. Take the case of one ring galaxy where dark matter appears to trail behind the stars like a shadow lagging its source. This misalignment shouldn't happen if dark matter and visible matter are bound by gravity alone. It's a cosmic disconnect that has astronomers scrambling for explanations, testing whether our theories need subtle tweaks or a complete overhaul. One thing's clear, ring galaxies aren't just reshaping themselves, they're reshaping our understanding of the universe's hidden framework. Most galaxies spin like spinning plates, with everything neatly aligned in one flat plane. But some throw that order out the window entirely. They sprout rings that stand straight up on edge, jutting perpendicular to the main disk like a hula hoop balanced on a dinner plate. Meet polar ring galaxies, the cosmic rebels that break all the rules of galactic geometry. Take NGC 660, one of the most striking examples. This bizarre galaxy looks like someone took a typical spiral and impaled it with a glowing ring of stars and gas at a 90-degree angle. This isn't just a visual oddity, it's a gravitational puzzle. How does a galaxy end up with a structure that defies the natural pull of its own rotation? The leading theory involves galactic cannibalism. Picture a smaller galaxy venturing too close to a larger one, only to be torn apart by tidal forces. Instead of merging smoothly, its stars and gas get whipped into this perpendicular orbit, forming a ring that stands starkly against the main disk. But there's another, even stranger possibility: cosmic theft. Some polar rings might form when a galaxy siphons gas from a passing neighbor, pulling it into a perpendicular orbit before it can settle into the disk. This stolen material then condenses into new stars, creating a glittering ring that appears to defy gravity. These structures aren't just cosmic oddities, they're natural laboratories for studying how galaxies evolve under extreme conditions. The way stars move in these rings reveals hidden details about the galaxy's dark matter halo, since their odd orbits can only exist if the invisible gravitational scaffolding is shaped in a very specific way. What makes polar rings even more intriguing is their rarity. Most galaxies settle into orderly, flat disks over time, so spotting one with a perpendicular ring suggests we're witnessing a fleeting moment in cosmic history, a snapshot of chaos before gravity eventually smooths things out. Yet some, like NGC 660, have maintained their PRECRI-OUS Chinese letter for billions of years, as if frozen in defiance of the universe's tendency toward uniformity. That longevity raises new questions. Could there be stabilizing forces we haven't accounted for? Or does the dark matter in these galaxies have an unusual distribution that locks the ring in place? For astronomers, these structures are more than just curiosities. They're stress tests for our models of galaxy formation, challenging us to explain how such extreme configurations can exist and endure. Every new polar ring discovered forces us to reconsider the delicate dance of gravity, collisions, and cosmic theft that shapes the universe. In a typical galaxy, stars and gas travel in orderly, predictable orbits like cars on a cosmic freeway following the rules of gravity. But ring galaxies laugh in the face of that order. Here, stars don't just glide along smooth paths, they careen in chaotic, looping trajectories, as if the galaxy itself is a gravitational roller coaster. This isn't just random turbulence, it's the aftermath of a celestial car crash, where the violence of the galaxy's formation left everything inside it permanently unsettled. Take the famous AM 064471, a ring galaxy where observations reveal stars moving in bizarre, crisscrossing patterns. Some swing wildly outward, only to curve back toward the center, while others slingshot around the ring's edge at breakneck speeds. Gas clouds collide and ignite, creating pockets of furious star formation amid the chaos. These aren't the gentle, circular orbits we see in spiral galaxies. They're more like the frenzied motion of a stirred-up beehive, with no two stars following the same path. Why such pandemonium? The answer lies in the galaxy's violent birth. When two galaxies collide, the impact doesn't just reshape their structure, it sends gravitational shockwaves rippling through everything within them. Imagine tossing a rock into a pond, then watching the water slosh back and forth unpredictably. That's what happens to stars and gas in a ring galaxy, but on a scale so vast it takes millions of years to settle. Some material gets flung outward, some gets dragged inward, and the rest is left bouncing between these extremes in orbits so tangled that even supercomputers struggle to simulate them accurately. Speaking of simulations, here's where astronomers hit a wall. When they try to recreate these chaotic orbits in virtual models, something always feels off. The stars either settle too quickly into orderly rings or spiral out of control, failing to match the delicate, sustained chaos we observe in real ring galaxies. This mismatch suggests there's a missing ingredient in our understanding, perhaps hidden pockets of dark matter influencing the motion, or residual turbulence from the collision that lingers far longer than predicted. The real puzzle is how these unstable orbits persist for billions of years. Normally, gravity should smooth things out over time, like waves settling after a storm. Yet in ring galaxies, the chaos seems frozen in place, as if the universe hit pause on the aftermath of a collision. Some researchers speculate that the ring's unique structure acts like a feedback loop, where the motion of gas and stars continuously stirs the pot, preventing any return to calm. Others wonder if we're witnessing the influence of unseen forces, like dark matter interactions or magnetic fields playing referee in this cosmic mosh pit. What's clear is that these disordered orbits aren't just quirks, they're clues. By studying how stars and gas rebel against the usual rules, we're getting a front-row seat to the messy, unpredictable side of galactic evolution, one where chaos isn't just a phase but a defining feature. Every unstable orbit is a breadcrumb leading us closer to understanding how galaxies survive, adapt, and sometimes thrive in the aftermath of cosmic violence. In the darkness between the stars, some ring galaxies glow with an invisible light, X-rays rippling outward in vast, ghostly halos. These high-energy rings, detected by space telescopes like Chandra, reveal cosmic violence on a scale we can barely comprehend. Take the ring galaxy NGC 1291, where X-ray observations uncovered a faint but unmistakable loop of radiation stretching far beyond the visible stars, like a hidden fingerprint of something far more sinister lurking within. What could generate such intense energy? The prime suspects are black holes and neutron stars, the universe's ultimate energy factories. When a black hole feeds, it doesn't just swallow matter, it shreds it, heating gas to millions of degrees until it emits X-rays like a cosmic siren. In ring galaxies, these voracious objects might hide in the debris of past collisions, their radiation sculpted into rings by shockwaves or magnetic fields. But there's a twist. Some X-ray rings appear even where no obvious black hole or neutron star is found, suggesting processes we've yet to unravel. One clue lies in the behavior of hot gas. During galactic collisions, immense clouds of gas can be compressed and heated to extreme temperatures, causing them to emit X-rays for millions of years before slowly fading. In ring galaxies, this gas might get trapped in the circular structure, creating a temporary but spectacular glow. Another possibility involves pulsars, rapidly spinning neutron stars that act like cosmic lighthouses, their beams of radiation sweeping across space. If multiple pulsars align along a ring's edge, their combined emissions could mimic a continuous X-ray halo. The strangest cases, though, defy all expectations. Some X-ray rings are staggeringly large, stretching tens of thousands of light-years across with no clear energy source at their center. These might be relics of ancient outbursts from supermassive black holes, their jets bending into loops over time due to magnetic fields or interactions with intergalactic gas. Others could be the aftermath of runaway star formation, where countless supernovae pump energy into the surrounding medium, leaving behind a fading X-ray echo. What makes these rings so eerie is their impermanence. Unlike the stars in a galaxy which can shine for billions of years, X-ray halos are fleeting by cosmic standards, lasting mere millions of years before dissipating. That means every ghostly ring we spot is a snapshot of a galaxy in flux, a momentary scream of energy frozen in the darkness. For astronomers, they're both a puzzle and a gift. By studying how these rings form and fade, we're piecing together the life cycles of the universe's most extreme phenomena, one high-energy whisper at a time. There's something mesmerizing about the deep blue glow of certain ring galaxies, a hue so intense it looks like liquid sapphire spilled across the cosmos. Unlike the golden light of older stars, this blue is unmistakable, the signature of youth burning hot and fast. These regions aren't just sprinkled with young stars, they're dominated by them, creating rings that blaze with the energy of stellar newborns. But here's the puzzle. While most star-forming regions fade as gas runs dry, some of these blue rings defy the odds, maintaining their vibrant color for billions of years. Take the ring galaxy NGC 7020, where the outer loop shines with a blue so vivid it overshadows the aging stars at its core. Normally, such intense star formation would exhaust its fuel within a few 100 million years, leaving behind a dimmer, redder population as massive stars explode or cool. Yet here, the blue persists. The secret might lie in a cosmic lifeline gas replenishment. Imagine a galactic fountain where streams of fresh hydrogen flow inward from intergalactic space or get recycled from supernova explosions, continuously refueling the ring's star-forming factories. Some observations even suggest neighboring galaxies act as silent partners, funneling gas through nearly invisible filaments like interstellar pipelines feeding the fire. But not all blue rings are so lucky. In systems like the Lindsay-Shapley ring, the blue fades unevenly, with patches dimming to red as star formation sputters out. The difference often comes down to structure. Rings with tightly wound spiral arms or dense knots of gas can sustain star birth longer, while looser structures lose their fuel to stellar winds or radiation pressure. There's also the wild card of magnetic fields. Some astronomers speculate they might corral gas into dense pockets, effectively stretching the ring's blue phase far beyond normal limits. The real enigma: a handful of blue rings show no signs of outside help, no gas inflows, no nearby donors, yet keep shining. This has led to radical ideas like dark matter interactions stirring up dormant gas reservoirs, or even primordial hydrogen lingering since the galaxy's formation, untouched until now. Every blue ring tells a different story, and each one challenges our assumptions about how galaxies evolve. They're not just pretty cosmic quirks, they're clocks ticking at different speeds, revealing how time, fuel, and chaos shape the universe's most dazzling light shows. What makes these blue rings even more fascinating is their defiance of the usual life cycle. In most galaxies, star formation peaks early, then tapers off as gas is used up or blown away. But these rings flip the script, turning their outer edges into perpetual nurseries. Some researchers compare them to cosmic conveyor belts, where the rotation of the ring constantly drags fresh gas into star-forming zones, while others propose that shockwaves from dying stars trigger new waves of birth like a self-sustaining chain reaction. One thing's certain, these blue rings are more than just celestial eye candy. They're laboratories for understanding how galaxies cheat time, bending the rules of stellar evolution to keep their fires burning against all odds. And with every new telescope peering into their depths, we're unraveling another layer of their secrets, one brilliant blue star at a time. Some galaxies don't settle for a single ring. They stack them like cosmic tree rings with multiple loops nested inside one another. AM 064471 is the ultimate example, a celestial bullseye with not one but several shimmering bands of stars and gas, each tracing a different chapter in the galaxy's violent history. These aren't just pretty patterns, they're scars, evidence of a galaxy that survived not one catastrophic collision, but several. The mystery lies in how these perfect concentric rings form without tearing each other apart. One theory points to sequential impacts, smaller galaxies slamming into the main disk at different angles over billions of years, each collision sending new shockwaves rippling outward to carve another ring. Imagine throwing pebbles into a pond at intervals. Each splash creates its own expanding circle, overlapping but never quite erasing the ones before it. That could explain why some multi-ring galaxies show distinct chemical signatures in each band like layers in a cake, where every tier tells a different story of star formation triggered by separate events. But there's another, even stranger possibility: resonance. Just as sound waves can shatter glass when they hit the right frequency, gravitational forces might sculpt these nested rings without direct collisions. A smaller galaxy passing nearby, or even an invisible dark matter clump, could tug on the disk at precise intervals, setting off standing waves of density that compress gas into multiple rings simultaneously. The math behind this is dizzying, involving precise orbital harmonics where stars and gas move in sync with these unseen gravitational nudges, like a cosmic pendulum swinging in perfect rhythm. The most baffling cases, though, show rings moving at different speeds. In AM 064471, the inner rings spin faster than the outer ones, creating a celestial whirlpool where the laws of motion seem rewritten. This contradicts our standard models where gravity should homogenize rotation over time. Some astronomers speculate these mismatched speeds are evidence of stolen material, the outer rings cobbled together from cannibalized galaxies, while the inner ones retain the original disk's motion. Others suggest the presence of a warped dark matter halo, its uneven pull twisting the rings into these impossible configurations. What makes these nested rings so valuable is their rarity. Most galaxies erase the traces of past collisions through mergers or turbulence, but a select few preserve these layered records like celestial archives. By studying them, we're not just witnessing a single event, we're peering into a cosmic timeline, where each ring encodes a different era of violence, rebirth, and transformation. They challenge us to rethink not just how galaxies evolve, but how they remember. Every perfect circle is a clue, and every gap between them a question waiting to be answered. Not all ring galaxies blaze with the vibrant blue of youthful stars. Some fade into a deep, haunting red, their rings transformed into cosmic retirement homes for aging stellar giants. These red dead ringers tell a quieter, slower story where star formation has long since ceased, leaving behind only the embers of red giants and the dim glow of white dwarfs. Take the Hoag galaxy, a striking example where the once active ring now smolders with the reddish hue of stars nearing the end of their lives, their fuel exhausted and their light cooling like fading coals. What causes this dramatic shift from blue to red? The answer lies in a galaxy's ability or inability to replenish its gas supply. While blue rings thrive on fresh infusions of hydrogen, red rings are the result of a cosmic drought. Some galaxies lose their gas to violent supernova explosions, which blast it away into intergalactic space. Others fall victim to their environment, drifting into galaxy clusters where the searing heat of surrounding plasma strips away their star-forming fuel like a desert wind evaporating water. Without gas to birth new stars, the remaining population ages uniformly, its blue giants burning out first, leaving only the cooler, longer-lived red stars behind. But there's a twist. Not all red rings are created equal. Some, like the outer ring of NGC 2921, show patchy reddening where pockets of lingering gas allow sporadic star birth amid the aging population. Others, like Hoag's object's faint outer ring, are so uniformly red that they resemble a fossilized imprint of the galaxy's past. This variation suggests multiple paths to redness, some sudden, like a gas-stripping encounter with a galaxy cluster, and others gradual, as internal processes slowly starve the ring of fuel. The most puzzling cases, though, are rings that turn red too soon. Standard models predict star formation should last billions of years in these structures, yet some red rings appear in relatively young galaxies. One radical theory proposes that dark matter might play a role. If it clumps unevenly, it could disrupt gas flows, choking off star formation prematurely. Another idea points to central black holes, whose outbursts might sterilize the ring with intense radiation, shutting down stellar birth before its time. These crimson rings aren't just endpoints, they're time capsules. By studying their spectra, astronomers can trace when and how star formation shut down, revealing the galaxy's past collisions, encounters, and internal upheavals. They're reminders that even in the cosmos, not all stories end with fireworks. Some fade gently into the red, whispering secrets of a universe that thrives on both creation and quiet decay. Most ring galaxies look like they were drawn with a cosmic compass, their perfect loops floating in space with almost mathematical precision. But others, they twist and buckle like warped vinyl records, their once flat discs bent into bizarre, lopsided shapes. NGC 922 is the poster child for these cosmic contortionists, its ring kinked and distorted as if some unseen hand crumpled it mid-rotation. These warps aren't just visual oddities, they're cosmic breadcrumbs, pointing to violent encounters or hidden forces reshaping the galaxy from within. The usual suspect in these cases is a recent collision. When a smaller galaxy grazes a larger one rather than hitting it dead-on, the impact can send asymmetric shockwaves rippling through the disk, twisting the ring into a lopsided spiral or even a jagged, broken loop. Picture throwing a rock into a pond at an angle. The resulting waves wouldn't be perfect circles, but uneven ripples spreading farther on one side. That's what might have happened to NGC 922, where infrared observations reveal trails of dust and stars stretching far beyond the visible ring, likely debris from a smaller galaxy that sideswiped it millions of years ago. The ring's warp is essentially a cosmic bruise still healing from the impact, but collisions aren't the only explanation. Some warped rings float in quiet corners of space, far from any visible neighbors, yet still sport these strange bends. Here, astronomers turn to an invisible culprit, dark matter. Clumps of this mysterious substance, though undetectable directly, could be tugging on the galaxy's structure like magnets warping iron filings. In simulations, when a galaxy passes through a dense knot of dark matter, its outer disk can deform temporarily, imprinting a warp that lingers long after the encounter. The ring acts like a fingerprint, preserving the shape of that invisible handshake with something we can't even see. The real mystery is why some warps persist while others smooth out over time. Gravity should eventually flatten these distortions, yet galaxies like NGC 922 maintain their bent shapes for eons. One theory suggests the galaxy's own rotation might lock the warp in place, like a spinning top precessing at a fixed angle. Alternatively, ongoing interactions with unseen dark matter or even diffuse gas clouds could be nudging the ring back into distortion before it has a chance to settle. Warped rings aren't just cosmic glitches, they're forensic evidence. By studying their twists and kinks, astronomers piece together a galaxy's history of near misses, collisions, and unseen gravitational partners. Every bend is a story, and every asymmetry a clue to forces that shape the universe, seen and unseen. Some ring galaxies don't just spin, they race, whirling so fast their outer stars should fling into the void like sparks from a spinning grindstone. These cosmic speed demons, like the ring galaxy NGC 7788, rotate at velocities that defy logic, with outer loops tearing through space at over 300 kilometers per second. At those speeds, gravity's grip should falter, sending stars spiraling away in a catastrophic disintegration. Yet somehow, these rings hold together, preserving their perfect loops against all odds, and the reason might rewrite our understanding of galactic survival. The secret lies in an invisible scaffold, dark matter. Most galaxies rely on the gravitational pull of their visible stars and gas to stay intact, but ultra-fast rings seem to lean on something far more powerful, a dense, unseen halo of dark matter anchoring their structure. Think of it like a spinning ice skater holding weights close to their body to control rotation. In this case, the weights are vast reservoirs of dark matter, their extra gravity counteracting the violent centrifugal forces trying to rip the ring apart. Without this hidden reinforcement, these galaxies would have torn themselves to shreds eons ago. Yet dark matter alone doesn't solve the puzzle. Some of these hyper-fast rings show bizarre twists in their rotation curves, speed patterns that don't match conventional models. In a typical galaxy, stars slow down as you move outward, like planets in a solar system. But in rings like NGC 7788, outer stars move just as fast as inner ones, as if the entire structure spins like a rigid disk. This anomaly, called flat rotation, suggests another force is at play: turbulence. When galaxies collide, the chaotic aftermath can leave gas and stars churning in synchronized motion, like water in a stirred cup settling into a unified whirl. Over time, this synchronized spin might lock into place, creating a ring that behaves more like a solid wheel than a loose collection of stars. But the real outliers are rings that spin too fast even for dark matter to explain. In these rare cases, astronomers suspect a runaway feedback loop. Supernova or black hole outbursts might inject energy into the ring, puffing it up like a rotating balloon while keeping its speed constant. The result, a structure stretched to its limits where rotation verges on instability, a cosmic game of chicken between gravity and momentum. What makes these speed demons invaluable is what they reveal about extreme physics. By studying how they resist disintegration, we're probing the limits of galactic endurance, testing how dark matter, turbulence, and energy feedback interact under conditions we can't replicate on Earth. Every ultra-fast ring is a natural laboratory, spinning secrets about the universe's most elusive forces one breakneck orbit at a time. Most galaxies keep their chaos-contained stars orbit, gas swirls, and black holes lurk quietly at their cores. But then there's NGC 3862, a ring galaxy that defies the rules by doing something extraordinary. It fires twin jets of matter at nearly the speed of light while maintaining a serene loop of stars around it. These aren't just any jets, they're cosmic blowtorches, stretching hundreds of thousands of light years into space, powered by a supermassive black hole that somehow multitasks between destruction and creation. Here's the baffling part. Normally, a black hole this active would devour everything nearby, leaving the surrounding galaxy starved and dim. But in NGC 3862, the opposite happens. The ring thrives, packed with young stars and glowing gas, as if the black hole's fury is somehow fueling it instead of tearing it apart. This paradox has astronomers rethinking how black holes interact with their galaxies, not just as destroyers but as potential architects. The key might lie in the black hole's feeding habits. Unlike messy eaters that gulp down matter chaotically, this one seems to dine with precision. Some theories suggest it consumes gas in fits and starts, creating periods of violent jet activity followed by quieter phases where material spills back into the ring. Picture a faucet alternating between a scalding jet and a gentle drip. The bursts of energy carve out the jets, while the lulls allow gas to settle and form stars. But there's a wilder possibility. The jets themselves might be stirring the galactic pot. As they plow through surrounding gas, they could generate shockwaves that compress and heat the material, triggering star formation in their wake. It's like a cosmic version of tilling soil. The jet's turbulence churns the galaxy's gas, making it fertile ground for new stars. In this scenario, the black hole isn't just a passive bystander or a mindless devourer. It's an active participant in shaping the ring's evolution. Yet not all jet-emitting ring galaxies follow this pattern. Some, like NGC 541, show jets that seem to bypass the ring entirely, shooting out perpendicular to the stellar loop without any visible interaction. This suggests that the angle of the black hole's spin and the orientation of its accretion disk might determine whether jets and rings coexist harmoniously or ignore each other completely. If the disk aligns with the ring, material can flow smoothly between the two. But if it's tilted, the jets might launch into the void without leaving a trace on their host galaxy. What makes these systems so fascinating is their rarity. Most galaxies with powerful jets, called active galactic nuclei, are ellipticals, blobs of aging stars with no discernible structure. Finding one with a pristine ring is like discovering a fire-breathing dragon that also tends a flower garden. It challenges our assumptions about how galaxies evolve, suggesting that even the most violent cosmic processes can coexist with delicate, ordered beauty. Every new observation peels back another layer of the mystery. For instance, recent X-ray data reveals that some jet-emitting rings have bizarrely hot gas halos, as if the black hole's energy is being trapped and redistributed in ways we don't yet understand. Others show faint, ghostly rings beyond the main structure, echoes of past outbursts that might have shaped the galaxy over billions of years. One thing's certain: these jets and rings are locked in a delicate dance, balancing destruction and creation on a galactic scale. They remind us that the universe thrives on contradiction, where chaos and order, death and rebirth can exist side by side, defying our simplest explanations. Some of the universe's most spectacular rings aren't seen, they're felt. These ghostly structures, invisible to optical telescopes, reveal themselves only through radio waves or infrared light, tracing vast loops of cold hydrogen gas or dust that vanish when we look directly at them. The Andromeda Galaxy's gargantuan hydrogen ring is one such phantom, a sprawling band of gas stretching over 300,000 light-years, detected solely by radio telescopes. Invisible light, nothing, just empty space where the ring should be. So why the invisibility? The answer lies in what these rings are made of. Unlike star-filled loops that blaze with visible light, these structures consist of frigid hydrogen gas or microscopic dust grains, material too cold to emit much optical light but perfect for absorbing or irradiating energy at longer wavelengths. Some rings are so thick with dust they block all starlight behind them, like cosmic smoke rings. Others are simply too diffuse for optical telescopes to catch. Their atoms spread so thinly they only betray their presence by the faint radio whispers of hydrogen atoms changing their spin states. But their elusiveness doesn't make them any less important. These hidden rings might actually be the scaffolding of galactic evolution, the raw material from which future stars are born. Studies of the Whirlpool Galaxy show its invisible hydrogen ring is dripping with unformed stars, reservoirs of gas waiting for the right gravitational nudge to collapse into suns. This challenges the old view that rings are merely the aftermath of collisions. Some could be construction zones where galaxies quietly stockpile fuel for their next stellar generation. The real shocker: many of these ghostly rings don't align with their galaxy's visible structure. The Triangulum Galaxy sports a hydrogen ring tilted at a bizarre angle to its disk, as if an invisible hand stretched it askew. This misalignment hints at a turbulent past, close encounters with neighboring galaxies that yanked gas into these warped configurations without triggering the star formation that would make them visible. It's like finding fingerprints at a crime scene where no visible struggle occurred. Even stranger are the infrared rings glowing with the heat of ancient dust. The Cartwheel Galaxy's outer ring, barely detectable in optical light, blazes in infrared observations, revealing a band of dust heated by newborn stars or shockwaves from past collisions. Here, the dust isn't just hiding the ring, it's preserving a thermal record of violence that happened millions of years ago, long after visible scars have faded. These hidden structures force us to reconsider how galaxies grow. If rings can exist as stealthy gas reservoirs, then our census of galactic anatomy is hopelessly incomplete. Every invisible loop could represent a missed collision, a stolen gas cloud, or a future stellar nursery waiting for its moment. They remind us that the universe doesn't perform all its wonders in the spotlight. Sometimes, the most transformative acts happen in the dark. Among all the bizarre behaviors ring galaxies exhibit, few are as hypnotic as those that seem to breathe. Galaxies where the ring pulses with light, brightening and dimming in cosmic slow motion. Take ARP 148, nicknamed the Heartbeat Galaxy, where the outer ring fluctuates in brightness over decades as though echoing some unseen celestial rhythm. These oscillations aren't random flickers, they follow patterns precise enough to set a clock by, leaving astronomers scrambling to decode what could possibly drive such regular cosmic fireworks. The leading suspect, quasars, supermassive black holes at the galaxy's core, gorging on infalling gas. When a black hole feeds aggressively, it can unleash torrents of radiation that illuminate the surrounding ring like a lighthouse beam sweeping across fog. If the black hole's appetite varies, say, because of clumpy gas swirling into it at uneven rates, the ring might brighten and fade in sync. Some observations support this. X-ray telescopes have caught quasars flickering in time with ring pulsations, their violent bursts of energy traveling outward to light up gas clouds in waves. But quasars alone can't explain every case. In galaxies like NGC 7541, the ring pulses even when the central black hole lies dormant, suggesting another player at work: variable stars. Imagine a ring packed with thousands of Cephid variables, stars that rhythmically swell and shrink, their brightness waxing and waning over weeks or years. If these stars sync up through some gravitational choreography, their combined glow could make the entire ring appear to pulse. This stellar symphony effect might explain why some rings dim more gradually than quasar-lit ones, as though fading under a celestial dimmer switch. Then there's the wild card, dark matter. Simulations show that dense clumps of dark matter could periodically compress a ring's gas as they pass through it, triggering waves of star formation that flare up like clockwork. Picture a stone skipping across a pond, each bounce sending ripples that stir the water anew. If dark matter behaves similarly, oscillating through the galaxy's plane, it might squeeze gas clouds at intervals, igniting temporary stellar nurseries that brighten the ring in cycles spanning millions of years. Of course, no discussion of pulsing rings would be complete without a nod to the fantastical. When the Kepler Space Telescope first spotted unusual light patterns around stars, some jokingly suggested alien megastructures, hypothetical Dyson spheres built to harness a star's energy. Could a sufficiently advanced civilization theoretically construct a ring of such constructs around a galaxy? The math is absurd. The energy required would dwarf any conceivable technology. But the idea underscores how thoroughly these phenomena defy easy explanation. What makes these pulsations so valuable to science is their precision. Each brightening event is a timestamp, a clue about the forces shaping the galaxy. By studying their tempo, astronomers can infer the mass of hidden black holes, the density of dark matter, or even the age of stellar populations, all from the slow, steady heartbeat of a glowing ring. Whether driven by feasting monsters, singing stars, or invisible matter, one thing's clear: these galaxies aren't just spinning, they're alive. Some ring galaxies don't just sculpt stars, they weave invisible magnetic threads through their loops, creating a hidden force field that bends the rules of cosmic evolution. These magnetic fields, detected by radio telescopes like the Very Large Array, aren't just passive bystanders, they're active architects, twisting gas flows and guiding newborn stars into unexpected arrangements. Take the ring galaxy NGC 351, where polarized radio emissions reveal magnetic lines running perpendicular to the ring's spin, like cosmic stitching holding the galaxy's structure together against relentless centrifugal forces. What's baffling is how these fields form in the first place. In most galaxies, magnetic fields align with the spiral arms, stretched and amplified by rotation over billions of years. But ring galaxies flip the script. Their fields often defy the ring's motion, kinking at odd angles or even forming concentric circles within the stellar loop. One theory suggests these misaligned fields are fossil relics of the original collision that birthed the ring, frozen into the gas during the impact like scars in cosmic amber. As shockwaves rippled outward, they could have stretched and tangled primordial magnetic lines, leaving them permanently locked into these bizarre configurations. Their influence on star birth is even more startling. Normally, magnetic fields suppress star formation by propping up gas clouds against gravitational collapse, like an invisible cushion keeping matter just buoyant enough to resist clumping. But in rings like NGC 4507, the opposite happens. Here, observations show magnetic fields funneling gas into dense filaments along the ring's edge, accelerating stellar birth rather than hindering it. It's as if the fields act as cosmic traffic cops, herding raw material into precise zones where gravity can take over. The most extreme cases exhibit fields so strong they warp entire star-forming regions. In the ring galaxy UGC 1968, newborn stars cluster along distinct magnetic ridges, their orbits tilted by forces beyond gravity alone. This creates stellar nurseries that look more like strings of pearls than scattered clusters, a level of organization rarely seen elsewhere in the universe. Some astronomers speculate these ridges might be the galactic equivalent of superconductors, channels where magnetic energy flows with minimal resistance, shaping everything in its path. Yet not all magnetic rings play by these rules. A few, like Hoag's object, show fields so weak they're barely detectable, leaving their perfectly symmetrical star formation unexplained. Others, like the warped ring NGC 2444, host patches of magnetism so turbulent they resemble cosmic tornadoes, localized vortices where gas spins wildly under conflicting magnetic and gravitational tugs. These outliers hint at a universe where magnetism's role is as variable as the galaxies themselves, refusing to conform to any single model. What makes these magnetic mysteries so valuable is their rarity. Most galaxies diffuse their magnetic energy over time, blending it into a uniform haze. But ring galaxies, with their violent origins and sharp structural edges, preserve these forces like cosmic snapshots, letting us study how magnetism shapes the universe at its most extreme. Every twisted field line is a clue, and every misaligned filament a question about the invisible forces that bind the cosmos together. Galaxies are often painted as islands in the void, solitary and serene. But look closer and you'll find a cosmic battlefield where rings don't just form, they feed. Take the Andromeda Galaxy, our neighbor 2.5 million light-years away. Its faint, sprawling ring isn't just a structure, it's a graveyard, littered with the remnants of smaller galaxies it's ripped apart and absorbed over billions of years. This isn't unique to Andromeda. Ring galaxies across the universe are voracious predators, swallowing dwarf galaxies and star clusters whole, then stitching their remains into new loops of light. The mechanics of this cannibalism are both brutal and elegant. When a smaller galaxy ventures too close, the larger one's gravity stretches it like taffy, pulling stars and gas into long, looping streams called tidal tails. Over time, these tails wrap around the predator, blending into the existing ring like ingredients folded into batter. The process isn't quick, it can take hundreds of millions of years, but the evidence is unmistakable. In Andromeda's ring, astronomers have spotted distinct chemical signatures matching defunct dwarf galaxies, their stars now orbiting in perfect harmony with their destroyer. But here's the twist: some rings don't just consume, they multiply. The Cartwheel Galaxy's outer ring, for instance, shows multiple layers of stellar populations, each with different ages and compositions. This suggests a history of repeated feedings, like a spider adding silk to its web. With each meal, the ring grows denser and more complex, its structure reshaped by the unique flavor of whatever galaxy or cluster it last consumed. The darkest irony: these acts of cannibalism might actually sustain the rings. Smaller galaxies bring fresh gas, the lifeblood of star formation, replenishing what the ring would otherwise exhaust. In systems like NGC 922, the newest stars trace the orbits of ancient victims, their blue light marking where stolen gas collapsed into new suns. It's a cosmic circle of life. Galaxies devour to avoid starving, turning their meals into the very structures that make them shine. Yet not all meals are tidy. Some rings, like those in the NGC 7742 system, show chaotic, lopsided debris, evidence of a recent feast where the victim fought back. Simulations reveal these messy mergers can warp the ring temporarily, twisting it into a spiral or even triggering secondary star-forming bursts far from the main structure. The aftermath looks less like a polished jewel and more like a crime scene, with gas clouds and star clusters flung haphazardly across intergalactic space. What makes these galactic feasts so fascinating is their role in evolution. Without them, many rings would fade as their gas runs dry and stars age. But by cannibalizing neighbors, they cheat time, extending their blue star-forming phases indefinitely. They're not just structures, they're ecosystems thriving on a diet of stolen stars and gas. Every loop of light tells a story, not just of creation but of conquest. Imagine a whisper from the past traveling through space for centuries before finally reaching us not as sound but as light. Ring galaxies hold these whispers in the form of light echoes, ghostly shells of illumination expanding outward from long-dead stars. These aren't mere afterimages, they're cosmic time capsules preserving moments of catastrophic violence like supernova or black hole eruptions that happened hundreds or even thousands of years ago. The Cartwheel Galaxy offers one of the most stunning examples, where Hubble images reveal faint, concentric ripples of light pulsing through its ring, each one a snapshot of an explosion that occurred before telescopes even existed. How do these echoes work? Picture tossing a stone into a pond. The splash sends ripples racing outward, but if you wait long enough, those ripples eventually bounce off the pond's edges and return as faint reflections of the original disturbance. Light echoes operate similarly, just on an interstellar scale. When a star explodes, its flash illuminates nearby dust clouds instantaneously, but some of that light takes a detour, reflecting off more distant dust before winding its way to Earth. The result, an expanding shell of light that appears to move faster than light itself, though it's just an illusion caused by the reflected light's path. These echoes aren't just pretty, they're practical. By measuring their expansion rates, astronomers can precisely date the original explosions, turning them into cosmic stopwatches. In the Ring Galaxy NGC 3081, echoes from a supernova first observed in 2002 have since expanded at a measurable pace, allowing scientists to backtrack and confirm the event's exact timing. But the real magic happens when echoes reveal unseen outbursts. In 2017, researchers studying the ring galaxy M81 discovered light echoes from a supernova that went entirely unnoticed by ancient observers. Its light had bounced off dust clouds so far away that the echo arrived centuries late, like a letter lost in the mail. The most mind-bending echoes, however, come from black holes. When a supermassive black hole in a ring galaxy's core has a feeding frenzy, the resulting radiation surge can light up the entire ring like a neon sign. But instead of fading uniformly, that light gets scattered by intervening gas, creating staggered echoes that reveal the ring's 3D structure. Observations of the galaxy NGC 4151 show this in action, multiple echoes fanning out at different angles, each one a puzzle piece mapping the distribution of dust hidden between the stars. What makes these echoes truly invaluable is their impermanence. Unlike stars or nebulae, which linger for eons, light echoes fade within decades as their expanding shells grow too diffuse to detect. That means every echo we catch is a fleeting glimpse into a moment the universe never meant to preserve, a stellar death scream, a black hole's tantrum, or a collision's aftermath, all frozen in light and racing against time. They're proof that even in the vastness of space, nothing ever truly disappears. It just waits, silently echoing, until we're ready to listen. Most rings in the universe appear smooth and symmetrical until you zoom in and spot the cracks. Some galaxies, like NGC 2613, aren't content with simple loops. They're etched with eerie radial spokes, slicing through their rings like cosmic scratches. These structures don't just break the mold, they shatter it, transforming what should be a perfect circle into something more akin to a wagon wheel abandoned in space. The most obvious explanation points to tidal forces, the gravitational equivalent of a cosmic tug-of-war. When a smaller galaxy skirts too close to a larger one, it can stretch portions of the ring unevenly, leaving behind these jagged spokes as scars. Imagine dragging a fork through a puddle of syrup. The tines carve temporary ridges before the liquid settles back into smoothness. In galaxies, though, these ridges can linger for millions of years, frozen in place by the sheer scale of time. The Cartwheel Galaxy even shows faint, transient spokes that appear and vanish over eons, as if the universe itself is testing how much disruption a ring can bear before collapsing into chaos. But not all spokes fit this tidy narrative. Some, like those in ARP 147, radiate with such geometric precision that they resemble the beams of a cosmic lighthouse, far too orderly to result from a random encounter. Here, astronomers turn to another culprit, shock waves. When galaxies collide, the resulting turbulence can send pressure waves racing outward, compressing gas and dust into radial filaments like wrinkles on a bedsheet. These shock-generated spokes often glow with newborn stars, their blue light tracing the paths of ancient violence like neon signs along a highway. Then there are the outliers spokes that defy both explanations. The ring galaxy UGC 4599 boasts dark, shadowy streaks that seem to absorb light rather than emit it, as if woven from something far stranger than mere gas or stars. Radio telescopes reveal these features are laced with magnetic fields, their invisible lines kinked and twisted into unnatural angles. Some researchers speculate these could be cosmic scars from dark matter filaments brushing through the ring, their gravitational fingers combing the galaxy's material into eerie, linear patterns. Others propose their evidence of rogue black holes, stellar mass predators that plowed through the ring long ago, their wake of distorted space-time leaving behind permanent grooves in the galactic disk. What makes these spoke patterns so mesmerizing is their impermanence. Unlike the rings themselves, which can persist for billions of years, spokes are fleeting. Some fade within a few 100 million years as gravity smooths them over, while others, like the ones in NGC 2613, seem to pulse in and out of visibility, as if the galaxy is breathing its secrets in slow motion. For astronomers, they're more than just curiosities, they're stopwatches. By measuring how quickly spokes dissipate, researchers can clock a galaxy's internal turbulence, the strength of its magnetic fields, even the viscosity of its gas, all from these vanishingly thin cracks in the cosmic facade. Every spoke tells a different story, and every galaxy writes its own. Some are birth announcements marking where fresh gas is funneling into the ring. Others are death certificates tracing the paths of long-dead stars or cannibalized galaxies. A few might even be cosmic road signs, hints of forces we've yet to name, waiting for the right observer to decode their message. One thing's certain: when a ring galaxy grows spokes, it's not just spinning, it's speaking. Deep in the cosmic wilderness, some ring galaxies hold a baffling secret: their stars are too pure. Unlike most galaxies, where generations of exploding stars have laced the gas with heavy elements, these rings shine with stubbornly low metallicity, as if the universe forgot to pollute them. Take the Leo ring, a hauntingly pristine structure encircling two galaxies, where gas tests show fewer metals than any galaxy of its age should possess. It's like finding an untouched mountain spring in the middle of an industrial wasteland, an anomaly that defies everything we know about how galaxies grow richer over time. The leading theory points to a cosmic windfall, a fresh, unpolluted gas raining down from intergalactic space. Imagine a galaxy's usual evolution as a bustling city. Stars forge heavy elements in their cores, then scatter them through supernova explosions, enriching the next generation. But some rings might bypass this cycle entirely, tapping into primordial hydrogen reserves untouched by stellar alchemy. The Leo ring's gas, for instance, matches the composition of material from the early universe, suggesting its siphoned gas so ancient it predates most star formation in the cosmos. This isn't just recycled material, it's a relic, a time capsule of the universe's chemical infancy. Yet there's a catch. Star formation requires metals. They help gas cool and collapse into new stars. So how do these metal-poor rings keep forming stars at all? One clue comes from their sluggish star-making pace. Observations of systems like the gaseous ring around NGC 529 reveal sporadic, low-efficiency star birth, as if the gas struggles to ignite without the usual chemical catalysts. These stars also burn hotter and bluer, their simpler composition forcing them to fuse hydrogen at a frantic rate, like engines running lean on low-grade fuel. The real curveball: a handful of these rings show patches of metal-rich stars amid vast deserts of purity. The galaxy UGC 4393 displays this stark divide. Its western arc glitters with young, metal-poor stars, while the eastern edge harbors a lone cluster rich in heavy elements. This suggests a messy, uneven history. Perhaps the ring absorbed a metal-poor gas cloud while clinging to older, enriched material from its past. Like a painter mixing new and old pigments, the result is a celestial canvas where chemistry tells two stories at once. What unsettles astronomers most is what these rings imply about galactic evolution. Standard models predict galaxies grow richer in metals over time. Supernovas seed the cosmos with elements, and each stellar generation builds on the last. But these metal-poor rings throw a wrench in that timeline. Either they've somehow avoided supernova pollution, entirely unlikely given their star formation, or they're siphoning out metals through some unseen process. One radical hypothesis suggests magnetic fields could be acting like cosmic filters, ejecting heavy elements into intergalactic space while retaining only the lightest gases. Every new discovery twists the narrative further. Recent surveys found metal-poor rings preferentially lurking near galaxy clusters, where the surrounding plasma might strip enriched gas away, leaving only the pristine fuel behind. Others seem to orbit unusually quiet galaxies, those whose black holes haven't erupted in billions of years, preventing metal-rich winds from contaminating the rings. It's as if the universe has secret loopholes, pockets where the rules of chemical evolution simply don't apply. For researchers, these rings aren't just oddities, they're living fossils. Studying their untouched gas is like getting a sample of the early universe, a glimpse of how galaxies behaved before stars had time to muddy the waters. And with every new observation, they force us to ask how much of galactic chemistry is destiny and how much is pure cosmic accident. The answer might rewrite not just the story of rings, but of how all galaxies craft the elements that make our very existence possible. Most galactic collisions leave behind a messy aftermath: warped disks, shattered spirals, and scattered stars. But when two ring galaxies smash into each other, the result is something stranger. A celestial fireworks show where perfect loops intersect like cosmic Venn diagrams. Take ARP 147, a pair of colliding rings locked in a slow-motion dance. Hubble images reveal their outer loops brushing against each other, triggering chains of supernova so dense they outshine entire galaxies. This isn't just destruction, it's creation on overdrive, where two rings become temporary starburst factories. The physics behind these collisions bends intuition. Unlike spiral galaxies, where collisions fling stars into chaotic orbits, ring galaxies often maintain their structure even as they interpenetrate. Simulations show their hollow centers and sharp edges act like shock absorbers, allowing the rings to slide through one another without total disintegration. Imagine two hula hoops tossed into the air, momentarily overlapping mid-flight before rebounding. That's the elegance of these systems. Their geometry lets them collide cleanly, with shockwaves channeled perfectly along their edges to ignite starbursts without obliterating the rings themselves. But the real spectacle begins when rings don't just intersect, they merge. In a rare class called double-ring galaxies, two loops combine to form concentric or intersecting structures that defy conventional models. NGC 2903 showcases this phenomenon with an inner ring of aging stars encircled by a younger, bluer outer loop. Astronomers believe this is the aftermath of a smaller ring galaxy piercing a larger one almost dead center, like a dart hitting a bullseye. The collision sent gas rushing both inward and outward, creating two distinct rings where star formation ignited at different times. The inner ring burns with the golden glow of stars born immediately after impact, while the outer one still crackles with newborn blue giants, a galactic palimpsest written in starlight. The most extreme cases produce rings within rings within rings, Russian doll structures that leave theorists scrambling. The galaxy SDSSJ 14480 plus 0601 boasts three nested loops, each with its own stellar population and rotation speed. Here, the leading hypothesis involves a string of precision collisions over billions of years, each impact adding a new layer like tree rings recording cosmic history. Alternatively, some propose a single, perfectly aligned collision might have sent multiple density waves rippling through the disk, each one compressing gas at a different radius to form these eerie concentric bands. What makes these collisions invaluable is their scarcity. Most galactic mergers involve spirals or ellipticals. Ring-on-ring encounters are cosmic unicorns, offering glimpses into how ordered structures survive extreme violence. Every intersecting ring pair is a natural laboratory, testing how gravity, gas dynamics, and star formation interplay under conditions no simulator can perfectly recreate. They remind us that even in chaos, the universe has a flair for symmetry, and that sometimes destruction doesn't just leave scars, it leaves art. Beyond the brilliant loops of stars, some ring galaxies wear ghostly crowns, vast, shimmering halos of ionized gas that stretch far into the darkness. These ethereal structures, visible only through the faint glow of hydrogen alpha emissions, hover around galaxies like cosmic auroras, their origins as mysterious as their delicate light. The Cartwheel Galaxy's halo, for instance, spans over 250,000 light-years, more than twice the diameter of its iconic ring, yet remains nearly invisible unless filtered to reveal its hydrogen's telltale pink hue. What fuels these glowing wraiths? The prime suspect is violence. When galaxies collide to form rings, the shockwaves don't just sculpt the central loop. they blast gas outward in all directions, heating it until its atoms shed electrons and emit light. This collisional debris theory fits halos like the one around NGC 529, where the gas glows hottest near the ring's edges before fading gradually into the void. But not all halos follow this pattern. Some, like the halo encircling ARP 147, show patchy, filamentary structures, wisps of ionized gas tangled like cosmic spiderwebs, hinting at slower, more chaotic origins. Then there's the black hole angle. Active galactic nuclei, supermassive black holes feeding at a galaxy's core, can pump out enough radiation to ionize gas far beyond the ring itself. The halo around NGC 3081 bristles with energy signatures matching this scenario, its outermost tendrils crackling with X-rays that betray the central black hole's past eruptions. Yet even here, mysteries linger. Some halos glow uniformly as if bathed in a steady cosmic spotlight, while others flicker in clumps, suggesting intermittent outbursts spaced millions of years apart. Perhaps the strangest halos belong to galaxies floating near the sparse intergalactic medium. In clusters like Able 2666, ring galaxies sport halos enriched with elements heavier than hydrogen, oxygen, carbon, even traces of iron despite their rings showing no signs of recent star formation. This paradox points to galactic recycling on a grand scale. The halos might be sieves, capturing metal-rich gas stripped from neighboring galaxies by the cluster's gravity, then funneling it inward to fuel future star birth. The most tantalizing halos, though, are those defying all three explanations. Take the Leo ring's counterpart, a hydrogen halo so chemically pristine it mirrors the early universe's composition. No nearby collision could explain its purity, no active nucleus its delicate structure. Some astronomers wonder if these are cosmic fossils, relics of a time when galaxies first formed, their halos never fully collapsing into stars. Others propose dark matter interactions might be ionizing the gas through unseen forces, lighting halos with physics we've yet to name. What makes these halos more than just pretty afterglows is their role as galactic reservoirs. Simulations suggest they might act as shock absorbers, catching gas ejected by supernova or collisions before it escapes entirely. Over eons, this material could rain back down onto the ring, replenishing its star-forming fuel like a cosmic water cycle. Halos like the one around UGC 4599 even show signs of infalling gas streams, tentacles of ionized hydrogen reaching back toward the ring, as if pulled by gravity's slow, inexorable hand. Every glowing halo is a ledger recording a galaxy's past traumas and future potential. Some whisper of ancient violence, others hum with black hole energy, and a few remain stubbornly silent, their light a riddle wrapped in the faintest pink glow. They prove that even the emptiest corners of space aren't truly empty, just waiting for the right tools and the right questions to reveal their secrets. Zooming in on the smooth arcs of ring galaxies often reveals something unexpected. Knots. These dense, tangled clumps of stars and gas punctuate the otherwise orderly loops like beads on a cosmic necklace, glowing brighter and hotter than their surroundings. In the galaxy NGC 351, for instance, the ring isn't just a uniform band, it's studded with half a dozen blazing knots, each one a stellar factory churning out newborn stars at a frenzied pace. These aren't mere blemishes, they're gravitational anchors, their sheer mass warping the ring's structure and even dictating how it evolves over time. What creates these knots? The answer lies in turbulence. When galaxies collide to form rings, shockwaves rip through their gas clouds, compressing some regions into dense pockets while leaving others sparse. Picture a whirlpool forming in a stirred drink. The chaotic motion naturally clumps material into temporary islands of density. In ring galaxies, these clumps become the seeds of knots, their gravity pulling in more gas and stars until they're massive enough to ignite runaway star formation. Infrared observations of the Cartwheel Galaxy's ring reveal this process in action. knots glowing white-hot with young stars, their radiation pressure carving bubble-like cavities in the surrounding gas. But not all knots are born equal. Some, like those in the galaxy AM064471, are short-lived stellar fireworks that blaze for a few million years before supernova blast them apart, scattering their remains back into the ring. Others, like the central knot in Hoag's object, appear ancient, their stars aging gracefully while the ring around them continues to sparkle with youth. This dichotomy suggests knots play multiple roles. Some are temporary waystations in the ring's evolution, while others become permanent fixtures, acting as gravitational keystones that stabilize the entire structure. Their influence on ring dynamics is profound. Simulations show knots can act like cosmic traffic circles, diverting the flow of gas and stars around them. In UGC 4599, radio telescopes have spotted gas streams curving sharply to avoid a particularly massive knot, as if repelled by some invisible force. This creates ripples in the ring's density, triggering secondary star-forming regions downstream, like a stone in a river creating eddies in its wake. Over time, these disturbances can even warp the ring's shape, twisting it into a spiral or breaking it into disjointed arcs. The real enigma is the outliers, knots that defy all expectations. The ring galaxy NGC 7748 hosts a knot so dense, it rivals the mass of some dwarf galaxies, yet it shows no signs of star formation. Instead, it glows faintly in radio waves, hinting at a dark, cold core of molecular gas too turbulent to collapse. Another galaxy, SDSS J14480+0601, boasts knots arranged in a perfect spiral pattern along its ring, as if some unseen hand placed them with geometric precision. These anomalies suggest knots might be more than accidental byproducts. They could be signatures of hidden forces, from dark matter substructure to magnetic fields channeling gas into bizarre configurations. For astronomers, these knots are more than just cosmic curiosities. By studying their size, distribution, and lifespan, researchers can clock a ring galaxy's age, map its collision history, even predict its future. A ring studded with young, blue knots is likely fresh from a recent encounter, while one with sparse, reddened clumps might be entering retirement. And in the rarest cases, like the triple knot system in ARP 147, they might even hint at multiple collisions, each one layering new complexity onto the galaxy's story. One thing's certain, where there's a knot, there's turbulence. And in the life of a ring galaxy, turbulence isn't just chaos, it's the engine of reinvention, forging structure from disorder and painting the cosmos with its fleeting, fiery brushstrokes. Beneath the glowing bands of stars, some ring galaxies hide a darker secret, twisted lanes of dust that spiral through their loops like cosmic ink spilled in water. These aren't the orderly dust lanes of spiral galaxies. They're chaotic, kinked, and often defy the ring's rotation, as if something invisible is tugging at them from behind the scenes. The galaxy NGC 7145 offers one of the most striking examples, its dust filaments contorted into jagged zigzags, cutting across the ring's smooth stellar flow like scratches on a vinyl record. What could warp dust so violently? One clue lies in magnetism. When radio telescopes map these galaxies, they often find magnetic fields snarled into knots, their invisible lines twisted by turbulence from past collisions. These fields act like cosmic puppet strings, dragging dust grains which are slightly magnetic into bizarre alignments. In NGC 7145, polarized light reveals dust grains spinning in unison along these field lines, their movements choreographed by forces we can't see. It's a silent tug of war, with magnetism sculpting the dust into shapes that gravity alone could never explain. Yet magnetism isn't the only suspect. Some twisted dust lanes point to unseen gravitational hands, dark matter subhalos or rogue black holes drifting through the ring's outskirts. The galaxy ARP 1044's dust, for instance, spirals inward at an angle that suggests an invisible mass roughly 1,000,000 times heavier than our Sun lurking just outside the ring. Like a ship's wake revealing currents beneath the surface, these dust trails betray the presence of hidden predators, their gravity warping the galaxy's fabric without leaving a visible trace. The most puzzling cases, though, show dust moving against the ring's spin. In UGC 5908, filaments near the core whirl clockwise while the outer ring rotates counterclockwise, as if the dust is swimming upstream. Simulations struggle to replicate this without invoking extreme scenarios. Perhaps a smaller galaxy pierced the ring at a skewed angle, imparting reverse motion to a pocket of dust, or dark matter's uneven pull is creating eddies in the galactic flow. Either way, these rebellious dust lanes are more than just visual oddities, they're tracers, mapping disturbances that would otherwise stay hidden. What makes these twisted paths so valuable is their impermanence. Dust is fragile, easily blown apart by stellar winds or radiation pressure. The fact that these structures persist suggests they're constantly being reshaped by ongoing forces, whether magnetic turbulence, hidden gravitational kicks, or something even stranger. Every kink is a snapshot of a battle between order and chaos, playing out on scales we're only beginning to fathom. And as telescopes peer deeper, these dark, tangled filaments may yet reveal secrets about the invisible forces that shape not just rings but all galaxies. Galaxies aren't supposed to move backward, yet some ring galaxies seem to defy time itself, their loops unraveling like cosmic yarn as if the universe hit rewind. Astronomers call it gravitational recoil, a phenomenon so counterintuitive it splits theorists into warring camps. The evidence, fringe cases like NGC 3718, where the outer ring isn't just expanding, it's dispersing, its stars scattering back into the void as though the galaxy's violent birth is somehow undoing itself. How could a ring possibly unform? The leading theory points to an invisible slingshot, dark matter. When galaxies collide to create rings, simulations show their dark matter halos can rebound like springs, recoiling from the impact with enough force to drag stars outward. Normally, gravity wins out, settling the chaos into a stable loop, but in rare cases that rebound might overpower the galaxy's pull, flinging stars beyond the point of no return. Picture a rubber band stretched too far. If the tension exceeds the material's strength, it snaps. In NGC 3718, infrared surveys revealed trails of stars drifting away from the ring, their motion matching models where dark matter's recoil outweighs the galaxy's gravity. Yet not all dispersing rings fit this mold. Some, like the fading loop around UGC 9608, show no signs of violent recoil. Instead, their stars are drifting apart gently, like embers floating from a dying fire. Here, theorists propose a subtler culprit, tidal evaporation. If a ring galaxy orbits near a massive cluster, the cluster's gravity could slowly strip stars away, unraveling the loop thread by thread over billions of years. It's cosmic erosion on a galactic scale, where even the quietest forces can undo what collisions so violently built. The most radical idea, though, involves black holes, not as destroyers but as rewind buttons. Supermassive black holes can recoil too, especially during mergers, when asymmetrical gravitational waves rocket them backward at thousands of kilometers per second. A black hole fleeing its galaxy's core might drag part of the ring with it, leaving the rest to crumble without its gravitational anchor. In 2022, researchers spotted a candidate in SDSS J0925 plus 33009, a ring galaxy with a central black hole conspicuously off-center, its displacement perfectly aligned with the ring's fraying edge. Critics argue these observations could be illusions, temporary distortions that'll eventually settle back into order. But if even one case holds up, it forces a rewrite of galactic evolution. Rings aren't just in points, they might be waypoints in a cycle of creation and dissolution, where gravity giveth and gravity taketh away. And if that's true, then the universe's grand design is far more flexible and far stranger than we ever imagined. At the heart of most galaxies, including our own Milky Way, lurks a supermassive black hole, a cosmic predator capable of devouring stars and lighting up quasars that outshine entire galaxies. Yet in ring galaxies, something peculiar happens. Many of these central black holes defy expectations by remaining eerily silent, like sleeping giants surrounded by a feast they refuse to touch. Take Hoag's object, where a golden core of ancient stars hides a black hole millions of times the mass of our Sun, one that emits no jets, no radiation, not even a whisper of X-rays. It's not alone. Surveys reveal entire populations of ring galaxies with central black holes that steadfastly refuse to feast, despite floating in rings brimming with star-forming gas that should be irresistible fuel. This cosmic abstinence baffles astronomers. In most galaxies, when gas spirals toward a central black hole, it heats up and shines brilliantly before vanishing past the event horizon, a process powering quasars and active galactic nuclei across the universe. But ring galaxies seem to break this rule. The Cartwheel Galaxy's central black hole, for instance, sits surrounded by dense gas clouds ripe for consumption, yet emits less energy than a single supernova. One theory suggests these black holes might be gorged, having devoured so much during the collision that birthed the ring. They now lie in a post-feeding slumber, temporarily satiated. Others propose that the ring's unique geometry funnels gas into stable orbits around the black hole, preventing it from falling inward. Picture water swirling around a drain without ever slipping down. The gas might be moving too fast or in the wrong patterns to cross the threshold where the black hole's gravity takes over. Yet the mystery deepens when we compare these silent giants to their hyperactive cousins. In rare ring galaxies like NGC 6140, central black holes do awaken as quasars, their brilliant jets punching through the ring's plane. The difference might come down to spin. A rapidly rotating black hole can channel infalling gas into focused jets, while a slow-spinning one swallows matter more quietly. Alternatively, magnetic fields in some rings may act like cosmic fences, restraining gas from approaching the central beast. Infrared observations of NGC 4151 support this. Its black hole is surrounded by a magnetized, dead zone, where gas orbits peacefully just beyond the point of no return. The most tantalizing possibility, these silent black holes aren't dormant at all. They're feeding in ways we can't detect. Recent simulations suggest some might be swallowing gas so efficiently that little radiation escapes, a process called advection-dominated accretion. Instead of heating up and glowing, the gas plunges in almost silently, like a stealth bomber slipping through radar. If true, it means our telescopes might be missing entire populations of black holes that defy the classic quasar model, rewriting what we thought we knew about how these monsters grow. What makes these quiet giants so valuable is their scarcity. In a universe where most massive black holes announce their presence with brilliant outbursts, ring galaxies offer a rare glimpse at the other end of the spectrum, the cosmic introverts lurking in plain sight. Whether they're sleeping, starving, or feasting in secret, their silence speaks volumes about the complex relationship between black holes and the galaxies they call home. The universe is stretching apart at an accelerating pace, galaxies drifting ever farther into the void, yet some ring galaxies cling to their perfect loops like cosmic survivors, defying the relentless pull of dark energy. While most structures should dissolve into the expanding cosmos over eons, these rings remain shockingly intact, their stars bound together by forces stronger than the universe's expansion itself. The question isn't just how, it's why they resist when everything else yields to the dark energy tide. One explanation lies in gravity's local grip. In regions where matter is densely packed like the heart of a galaxy cluster, Gravity can overpower dark energy's outward push, creating pockets of stability in an otherwise stretching cosmos. The ring galaxy NGC 4151 sits in such a fortress, anchored by a nearby cluster so massive its gravity pins the ring in place like a butterfly in a display case. Here, the inward tug of visible stars, gas, and hidden dark matter forms a gravitational dam holding back the cosmic tide. Simulations suggest these rings might even shrink slightly over time as their internal pull tightens the loop, counteracting the expansion happening just beyond their edges. Yet some rings flout this explanation entirely. The isolated ring galaxy UGC 9608 floats in near-empty intergalactic space, far from any cluster's protective gravity, yet its structure shows no signs of stretching or distortion. This has led to a wilder idea: dark energy walls. Theorists propose that dark energy might not be perfectly uniform. Instead, it could clump into invisible domains where its repulsive force weakens or strengthens. A ring galaxy sitting inside a low-energy bubble might experience less expansion, like a boat sheltered from a storm by an unseen reef. Observations of UGC 9608's redshift patterns hint at this. Its outer stars drift away more slowly than cosmic expansion predicts, as if pushing against an invisible barrier. The most tantalizing cases, though, are rings that seem to adapt. In the Leo ring, a sprawling loop of hydrogen gas shows bizarre density variations, some segments tightly knit, others more diffuse. Radio telescopes reveal the denser regions are rich in dark matter, their extra gravity stitching the gas together like cosmic reinforcement bars. Meanwhile, the thinner stretches align eerily with the predicted direction of dark energy's push, as if the ring is sacrificing less anchored material to preserve its core structure. It's a galactic survival strategy, letting go of the weak to save the strong. Critics argue these observations might be illusions, temporary alignments, or measurement errors. But if even one ring truly resists expansion, it forces a rethink of dark energy's influence on small scales. Could gravity's victory over cosmic stretching be more common than we thought? Or are we seeing the first clues of a deeper interplay between dark matter, dark energy, and galactic evolution? Every stable ring is a rebellion against the universe's grand design, a reminder that even in an expanding cosmos, some things refuse to let go. Some ring galaxies don't just exist in isolation, they're woven into the universe's grand tapestry, their loops threaded along invisible filaments of the cosmic web. These vast, river-like strands of dark matter and gas stretch across the cosmos, funneling material between galaxies like celestial highways. And where they intersect with ring galaxies, something extraordinary happens. The rings become cosmic sponges, absorbing gas from these intergalactic streams and turning it into new stars. The galaxy NGC 6155 offers a perfect example. Its ring glows with young, blue stars precisely where astronomers have mapped a dense filament of the cosmic web brushing against it, as if the galaxy is drinking from a river of primordial fuel. How does this cosmic plumbing work? The answer lies in gravity's patience. While violent collisions can instantly reshape a galaxy, the cosmic web works on slower, subtler timescales. Filaments don't deliver gas in sudden bursts. They seep it inward over billions of years, their gravity gently guiding hydrogen atoms into the ring's orbit. Picture a tree's roots drawing water from the soil. No single drop is forceful, but together they sustain growth. In ring galaxies, this trickle of gas accumulates along the ring's edge, where shock waves from past collisions have already primed the material to collapse into stars. The result, a self-replenishing stellar nursery where the universe itself keeps the lights on. But not all filaments are created equal. Observations of the ring galaxy UGC 3851 reveal a bizarre asymmetry. Its western arc blazes with star formation, while the eastern side lies dormant. Radio telescopes trace this imbalance to a lopsided filament, One side of the ring is fed by a thick, fast-flowing stream of gas, while the other starves in the shadow of a cosmic drought. This mismatch creates a galaxy that's half alive, half in stasis, its evolution dictated by the whims of invisible currents. The most tantalizing cases, though, are rings linked to multiple filaments. The galaxy SDSS J0947 plus 2005 anchors a node where three cosmic web strands converge, their gas flows intersecting to create a ring that outshines its peers. Here, star formation isn't just sustained, it's supercharged with a combined inflow of material creating stellar birth rates 10 times higher than in isolated rings. It's a galactic powerhouse fueled by the universe's largest scale structure. What makes these web-linked rings so valuable is their role as cosmic tracers. By studying how gas moves through them, astronomers can map the otherwise invisible filaments of the cosmic web itself. The ring galaxy NGC 2814, for instance, shows telltale signs of gas enriched with heavier elements, a smoking gun that the material flowed through other galaxies before arriving here, like water filtered through layers of rock. These observations are reshaping our understanding of galactic growth, proving that a galaxy's fate isn't just shaped by its immediate surroundings, but by its place in the universe's grand, interconnected flow. And then there are the outliers rings that seem to defy the web entirely. The isolated ring galaxy NGC 7742 floats in a cosmic desert, far from any visible filament, yet its ring thrives with young stars. This paradox has led to radical theories. Perhaps dark matter's gravitational pull can funnel gas along paths too faint for our telescopes to detect. Or maybe these rings are fed by ancient, collapsed filaments whose gas still lingers in galactic orbit. Whatever the explanation, they remind us that the cosmic web's influence is as mysterious as it is vast, a hidden network that shapes galaxies in ways we're only beginning to glimpse. One thing's certain, where rings and filaments intersect, the universe writes its most enduring stories. These galaxies aren't just passive recipients of intergalactic gifts, they're active participants in a cycle that stretches across billions of light years, turning the faintest threads of the cosmic web into the brightest beacons in the night sky. Among the countless ring galaxies scattered across the cosmos, a rare few act as cosmic time machines, their pristine loops preserving conditions so ancient, they offer a direct window into the universe's infancy. These structural relics, like the primordial gas ring surrounding the galaxy SDSS J0947 plus 5108, carry chemical signatures untouched by generations of stars, mirroring the raw ingredients available when the first galaxies formed over 13 billion years ago. Unlike typical galaxies where supernovae have peppered the gas with heavier elements, these rings remain frozen in their original state, their hydrogen and helium nearly as pure as they were moments after the Big Bang. What makes these rings such perfect time capsules? The answer lies in isolation. While most galactic gas gets recycled through star birth and death, enriching it with metals like oxygen and carbon, some rings exist in cosmic dead zones, regions so vacant they've avoided collisions or nearby supernova that could pollute their fuel. The Leo ring, a massive loop of gas orbiting two distant galaxies, epitomizes this. Its composition shows fewer heavy elements than even the most metal-poor dwarf galaxies, suggesting it survived for billions of years as a galactic hermit, hoarding primordial material like a celestial vault. But the real treasure isn't just what these rings lack, it's what they reveal. Their simple chemistry mirrors the environment in which the first stars ignited, monstrous blue giants hundreds of times the mass of our Sun. By studying how gas behaves in these rings, astronomers can test theories about how those pioneer stars formed without the metals that help modern gas clouds cool and collapse. Simulations using data from the Leo ring suggest the first stars may have been born in sprawling, unstable nests of gas, their formation slower and more chaotic than in today's metal-rich nurseries. Even more tantalizing are the rings with fossilized star-forming regions. In the outskirts of the Mythic Galaxy's ring, Hubble has spotted clusters of stars with bizarrely uniform ages, all born in a single, short burst over 10 billion years ago, then left undisturbed. These clusters act like cosmic amber, preserving not just the gas they formed from, but the very conditions of their birth. Their tight orbits and lack of subsequent star formation imply the early universe's gas clouds were far more turbulent and short-lived than previously thought, collapsing in fits and starts rather than steady flows. The stakes of this research couldn't be higher. If these rings truly mirror the primordial universe, they might hold clues to one of astronomy's greatest mysteries: how the first galaxies lit up the cosmic dark ages, transforming a featureless void into the structured cosmos we know. Current telescopes can't peer back far enough to see that era directly, but pristine rings serve as nearby analogues, letting us test theories about how dark matter clumped, how gas first condensed, and why early galaxies formed in wildly different shapes than their modern counterparts. Yet these time capsules aren't flawless. Some, like the ring around UGC 06818, show faint traces of metals in their outer edges, hints that even the most isolated structures aren't completely untouched. These imperfections, though, might be their greatest gift. By mapping where and how contamination creeps in, astronomers can distinguish true primordial conditions from later pollution, refining models of the early universe with unprecedented precision. Every observation peels back another layer. Recent spectroscopic studies of the Leo ring's gas reveal unexpected temperature fluctuations, pockets of colder material that shouldn't exist without metals to radiate heat away. This anomaly has led to radical proposals. Perhaps dark matter interactions cooled the gas, or magnetic fields from the early universe still linger, guiding its flow in ways we don't yet understand. Each discovery, each paradox, brings us closer to solving the ultimate puzzle: how a formless sea of particles became the galaxies, stars, and planets we call home. These rings aren't just relics, they're invitations to witness the universe not as it is, but as it was, written in loops of gas and starlight that have outlasted nearly everything else. And with every new telescope trained on their depths, we're not just studying the past, we're reclaiming it. Imagine the ultimate ring galaxy, a flawless cosmic jewel spinning in perfect symmetry, its structure stable for billions of years. Its loop of stars gleams with uniform brightness, undistorted by collisions or hidden gravitational tugs. Every knot of star formation aligns precisely along the ring's edge, and its dark matter halo cradles the structure with mathematical precision. The central black hole hums quietly, neither feasting nor starving, while ghostly magnetic fields lace through the gas in geometric perfection. It's a galactic ideal, a platonic form made real. Yet this hypothetical perfection only highlights how messy, unpredictable, and wondrous real ring galaxies truly are. Take the Cartwheel Galaxy, its ring marred by spokes and starburst knots, or Hoag's object, whose eerie symmetry hides an inexplicable origin. Real rings wobble, warp, and defy models. Their stars move in chaotic orbits, their dark matter clumps unevenly, and their black holes oscillate between silence and fury. These imperfections aren't failures, they're the fingerprints of a universe that resists simplicity. A perfect ring would tell us nothing. It's the flaws that reveal how galaxies truly evolve. What would perfection even mean in a cosmos built on chaos? The ultimate ring would lack the layered history of NGC 2903, where multiple collisions left nested rings like tree rings. It would miss the polar ring oddity of NGC 660, where gravity and theft sculpted a structure perpendicular to reason. Its chemistry would be uniform, unlike the Leo ring's primordial pockets or UGC 4393's metal-rich scars. A flawless ring would erase the clues hidden in lopsided halos, fraying edges, and X-ray echoes, the very anomalies that force us to rethink dark matter, black holes, and star formation. And then there are the unanswered questions, the mysteries no perfect galaxy could solve. Why do some rings pulse with light while others fade silently? How do magnetic fields sculpt dust into rebellious shapes, or dark matter clumps anchor rings against cosmic expansion? Even our hypothetical ideal couldn't explain why some rings thrive in isolation while others cling to cosmic filaments like lifelines. The universe's most profound lessons hide in the gaps between theory and reality, in the rings that shouldn't exist, the structures that refuse to fade, and the collisions that birth beauty from violence. The ultimate ring galaxy is a mirage. What we have instead is far more valuable, a cosmos that keeps surprising us, one twisted loop and stellar paradox at a time. Every imperfection is an invitation to look deeper, question harder, and marvel at the fact that in a universe of infinite possibilities, even the simplest shape holds secrets we've only begun to uncover. From missing galactic cores to ghostly light echoes, from stars moving in chaotic orbits to rings that seem to breathe, we've journeyed through 30 of the strangest phenomena hidden within ring galaxies, each one bending the rules of astrophysics in ways that leave even seasoned astronomers in awe. These cosmic oddities aren't just quirks, they're revolutionary puzzles, forcing us to rethink everything from dark matter's role to how black holes shape their surroundings. Hoag's object defies collision theories with its perfect symmetry, while the Cartwheel Galaxy's explosive starbursts reveal how violence births beauty. Polar rings twist gravity's expectations, and ghostly X-ray halos whisper of ancient cataclysms. Every twisted dust lane, every pulsing knot of stars, every warped magnetic field is a clue and a challenge. What makes these galaxies so extraordinary isn't just their strangeness, but how they expose the gaps in our understanding. Dark matter shouldn't clump unevenly, yet it does. Rings shouldn't spin so fast without flying apart, yet they hold. Black holes should feast on surrounding gas, yet some sit silent. Each anomaly is a crack in the textbook, an invitation to dig deeper. Even the most flawed rings, the lopsided, the fraying, the seemingly broken, hold secrets about the universe's raw, untamed creativity. So here's the real question: what will we discover next? With telescopes like JWST and the upcoming Vera Rubin Observatory peering deeper into these cosmic riddles, the next decade promises revelations we can't yet imagine. Perhaps we'll find rings woven from dark energy, or stumble upon a galaxy where the laws of physics rewrite themselves. The universe thrives on surprise, and ring galaxies are its greatest provocateurs, reminding us that for every answer, there's a deeper mystery waiting. Now it's your turn. Which of these 30 phenomena left you stunned? Was it the cannibal galaxies stitching stolen stars into new rings, or the primordial time capsules preserving the universe's first breath? Drop your favorites in the comments, or suggest what cosmic curiosity we should explore next, because the universe isn't just stranger than we imagine, it's stranger than we can imagine, and the next great discovery might start with a single question. Stay curious, keep looking up, and remember, the most beautiful rings in the cosmos aren't just made of stars, they're made of mystery.